Electrochemistry is one of the topics in this subject that will always be tested at KCSE, both in Chemistry Paper 1 and Chemistry Paper 2. In this short video, we take a journey through testing of the topic from the year 2018 to the year 2022 in Chemistry Paper 1, paper code 233/1. We begin with the year 2018, and this is question number 16. So we are told metal X and Y have standard electrode potentials of negative 0.13 and negative 0.76 volts respectively. We are told that the metals were connected to form a complete cell as shown in figure 4. So here we are, 1 molar of X ions as our electrolyte on the left. This is electrode X, voltmeter is here. Electrode Y, 1 molar Y ions as electrolyte on the left hand side. And then we have a piece of apparatus here, Z, which we call the salt bridge. So, to the questions, name the part labeled Z. Z is our salt bridge for 1 mark. Second question, that is part B, we are told to state one function of the salt bridge. So salt bridge completes the circuit. That is one function. Instead of using the word complete the circuit, a candidate can say that it provides, salt bridge provides an electrical contact between the electrodes. That is the same as completing the circuit. Second function of a salt bridge, though we are asked to just name one, the second function of a salt bridge is to provide cations and anions to replace those that are used up. So, for this part, a candidate was just asked to state one function. You can choose between those two for the next mark here. Finally, we were asked in part C to calculate the EMF of the cell, the electromotive force of the cell. So here, we normally use a formula. EMF of cell is given by E naught of the reduced half cell minus E naught of the oxidized half cell. We need to go back to our diagram so that we agree on which half cell will be reduced and which one will be oxidized. So this, we shall use the electrode potentials as our guide. Here, a candidate should just remember one word. The electrode with the most negative. I'm going for the most negative because here the values given are all negatives. So the guide is supposed to be that the electrode or the half cell with the most negative standard electrode potential, E naught value, this one we shall take to be the stronger reducing agent of the two. And we know from chemistry that a reducing agent is normally oxidized. So in this case, we will agree that Y has the most negative E0 value, what we call standard electrode potential. For that matter, Y is our strongest reducing agent between the two, and it will undergo oxidation as our X here gets reduced. So once we have known that, we can get back to our formula to be able to calculate the EMF of cell. But I want to make a correction here. The way the examiner drew the connected cell is probably not right, because we know that as we draw this diagram, the half cell which undergoes oxidation is the one that we usually put on the left hand side. This should have been our half cell Y, but the examiner drew it the other way around. Maybe to make the question a little bit more demanding for the candidate. But by convention, half cell Y would have been on the left because it is where oxidation shall take place, and X would have been on the right. Let's now move on and answer our question by calculating EMF. So we've agreed the reduced species is going to be our half cell X with a standard electrode potential of negative 0.13. From it, we shall subtract the standard electrode potential of half cell Y, which shall be oxidized. It has E0 value of negative 0.76. If we do the subtraction, we get a figure of positive 0.3 volts as our answer. It is 1 mark, a half for the subtraction, of course, the correct values, and a half for the final answer. We proceed now to the year 2019, question number 19. Given that the E0 of copper half cell is positive 0.34 volts and that of zinc half cell is negative 0.76 volts, we were asked to draw a labeled diagram of zinc and copper electrochemical cell. Now, before we draw, by convention, the half cell that undergoes oxidation is always the one that should be on the left hand side. So a candidate was to first determine between the copper half cell and the zinc half cell which one would undergo oxidation. And this is very easy to know. A student should just remember that the half cell with the most positive E0 value normally is the strongest oxidizing agent. The half cell with the most positive E0 value is usually the strongest oxidizing agent. Now we know from chemistry that oxidizing agents usually get reduced during reactions. So a candidate will just check between positive 0.34 and negative 0.76. Which of these two is most positive? And we agree it is positive 0.34. That is for the copper half cell. So the copper half cell would undergo reduction, and because of that, we would put it on the right hand side of our diagram, meaning that as we draw, we should start with a zinc half cell, the one that would undergo oxidation. So in this space, a student would just draw the half cell of zinc on the right hand side. So that is a beaker. Then we would introduce the electrode. The electrode would be a strip of zinc. The electrolyte would then follow, and here, because it is standard, we would use a solution that contains 1 mole of zinc ions. This first half cell would be connected to that of copper now via a salt bridge. That would do for the salt bridge, and then on this side we would now draw our copper half cell. We've just noted that it is the one that will undergo reduction. So we would have the copper strip here as our electrode, and then we would have again as electrolyte 1 mole of copper ions. Any solution that can provide that is used as electrolyte. Then we would join the electrodes now with a copper wire that is linked to a voltmeter. And a candidate was supposed to go ahead and show the direction of electron flow. Electrons usually flow from the anode to the cathode. Anode is the half cell where oxidation takes place. So this arrow would be the direction of electron flow. It is 3 marks, so the examiner would give half for the electrode on the oxidized half cell, half for the electrolyte, half for the electrode on the reduced half cell, another half for the electrolyte, a half for labeling the salt bridge. Of course, we are told to label. So a half for labeling the salt bridge, and last half would come from showing the direction of electrode or electron flow. That is what was expected in question number 19 for the year 2019. We then proceed to now the year 2020. Question number 7. Draw a labeled diagram of the setup of apparatus that can be used to electrolyze lead 2 bromide. This is now from Form 2, Electrochemistry 1. So lead bromide is a binary electrolyte, and before it can conduct electricity, we have to melt it. So we would put the solid lead bromide on a crucible, and then we would actually heat so that we obtain it in molten form so that our ions can be set mobile. So we'd have here molten lead bromide. Of course, after heating, that becomes our electrolyte. And then we shall introduce our electrodes into the electrolyte, of course inert, and we would then connect these to a cell, negative, or rather positive and negative, and that would do. We are told to label, so we shall label these two are our electrodes. We can use graphite if possible, and here we have our cell. We have the electrolyte being molten lead bromide, and of course we are showing the sign of heat here. So it is 3 marks, half for showing the cell, half for labeling the electrodes, a half for the electrolyte, and a half for heating. And then the last mark, to make them 3, would come from workability. So to earn the mark on workability, we are going to ask the question that the way you present your diagram, shall we be able to electrolyze lead to bromide? If the answer is yes, that your diagram meets the objectives of the experiment, you earn the 1 mark for workability. But if not, like for example, if you forget to put heat, that means the lead bromide will not be electrolyzed, and therefore you lose the mark on workability. Let's proceed on to question 21 for the year 2021, tested on metals, that is aluminum, and electrochemistry as well. So we are told aluminum is extracted from aluminum oxide through electrolysis. Part A, other than the cost of electricity, give another reason why this method is expensive. The method is expensive because the graphite used at anode, or the graphite used as anode, we are told when we are learning about aluminum extraction that it has to be replaced periodically. This is not a very cheap act because you have to buy the graphite more often. That would actually make the costs go higher. Now to part B, we were asked about the Faraday's law. And we are told to calculate the mass of aluminum obtained when 20 amperes is used for 5 hours. Of course, relative atomic mass of aluminum being 27, and 1 Faraday equals to 96,500 coulombs. The first thing a student should do here is to write the equation for deposition of aluminum from aluminum ion. So that is what would happen. It's either liquid or solid, doesn't matter, because we are depositing it from an aqueous solution. Now from here, we need to interpret this equation that for us to deposit 1 mole of aluminum, we need 3 moles of electrons. This is equivalent to 3 Faradays. So the meaning of this equation is that for 1 mole of aluminum to be deposited, which is equivalent to 27 grams, we need 3 Faradays, which is equivalent to 3 multiplied by 96,500 coulombs. So after writing this equation, we are able to interpret it this way. Next thing we do is now to go back to our question and look at quantity of electricity that we supplied. This is given by current in amperes, I, multiplied by time in seconds. So we have 20 amperes, that is our current. We shall multiply by 5 hours, but these 5 hours must be converted into minutes by multiplication by 60, and the minutes into seconds by multiplication by another 60. This gives us 360,000 coulombs. From here, we know that for us to deposit 27 grams, I need this number of coulombs. So then we argue out that if 3 by 96,500 coulombs is giving us 27 grams, how about the quantity of electricity that we supplied, which is 360,000 coulombs? This would give us how much? So cross multiplication would give 360,000 times 27. We divide by 3 times 96,500. This is supposed to give us only 33.5 0.75 grams of aluminium in 5 hours. 2 marks, half for calculating quantity of electricity, a half for the method used to obtain it, a half for the division, and a half for the final answer. Let's proceed to question number 7 for the year 2022. Determine the oxidation numbers of hydrogen in this formula. So here, what we do is that oxidation number of calcium, the first part, if we add to twice the oxidation number of hydrogen, because we have H2 here, we are supposed to get 0 because this is having no charge. Now, we know the oxidation number of calcium is supposed to be positive 2. So we replace it in our formula. Added to twice oxidation number of hydrogen, we should get 0. Now, subtracting 2 both sides, we would have 2 oxidation number of hydrogen giving us -2, and oxidation number of hydrogen alone being -2 divided by 2, and that gives -1. 1 mark, half for the relation that gives 0, and half for the answer. Moving to oxidation number of oxygen in OF2, we do the same. ON of O plus twice ON of F should give us 0. This time round, ON of O we do not know, but at least we know ON of F as -1. This should give 0. When we add 2 both sides, we get ON of O as +2. Half for the relation, half for the answer. Part B, write an ionic equation for the reaction between aqueous sodium hydrogen carbonate and ethanoic acid. Here, we need to start by writing a balanced chemical equation the normal way. That is my ethanoic acid, it is aqueous, reacting with sodium hydrogen carbonate, another aqueous solution. I'm supposed to get sodium ethanoate, CH3COONA, aqueous, and of course water as well, and carbon 4 oxide. It is a normal balanced chemical equation. So to get the ionic equation, I will need to split my aqueous solutions into the respective ions, starting with the first one. So in ethanoic acid, I have ethanoate ion in aqueous form and hydrogen ions as well. In sodium hydrogen carbonate, I have sodium ions and the hydrogen carbonate ion. Moving on to my product, I'll have again the ethanoate ion and sodium ion. And of course in water, I have no ions, I leave it the way it is, and in carbon dioxide gas, I have no ions. After I've done this, what remains is to strike off spectator ions, those that appear on both sides. So sodium ions will go and the ethanoate ions. Those are what we call spectator ions. So to get the ionic equation, I need to rewrite these excluding the spectator ions. So I have hydrogen ions reacting with carbonate ions, and we form water and carbon 4 oxide. That becomes my ionic equation for 1 mark. Let's finally look at the year 2022 question number 12, which also tested the topic electrochemistry. Products of electrolysis at the electrodes for aqueous solutions depend on three factors. Two of these factors are concentration of electrolyte and nature of electrode. The examiner asked us to name the other factor, which would make them three. And this is as easy as position of ion in question or element in what we call electrochemical series. Just as discussed in another question within this video. For part B, complete table 3 to show products of electrolysis for dilute calcium chloride and concentrated calcium chloride at anode and cathode. So we shall begin with the ions present. Calcium ions are there, chloride ions are there, hydroxyl ions are there, and we have hydrogen ions. So when it comes to dilute calcium chloride, at anode, we will discharge the OH radical the normal way. And when you do so, the gas that comes out is oxygen. At cathode, we shall discharge our usual hydrogen ions to get hydrogen gas. Now when it comes now to the concentrated calcium chloride at anode, we will now not discharge hydroxyl ions because of their low concentration, but we shall now discharge chloride ions due to their higher concentration. So we shall then get chlorine gas instead of oxygen when we use concentrated calcium chloride. For the cathode, concentration will have no effect, so we shall still get hydrogen gas after discharging hydrogen ions. With that, we've come to the end of our video where we have reviewed the topic electrochemistry as tested for the past 5 years.